Okay, thank you. A long title and hopefully short talk, right? So I'm Zoltán Juhász, and this is talk about our collaborative research work with the Wigner research group. And I won't read the title again. So this is plasma physics, and I won't go into the physics part because this is a GPU conference. So I want to concentrate on the GPU part. But just to give you some context, the problem is a three-dimensional plasma geometry. Luckily, this magnetized plasma, oh, that was very quick. I said short talk, sorry. So I pressed the wrong button. This is not good. So the point is it can be simulated in 2 dimensions in a cross section somewhere there. This is the cross section. And in the center, we have a particle source. So we inject particles with a predefined rate. We have magnetic force acting on the particles, and we also have a density probe. Okay, so this is what physicists want to simulate, and I'll tell you in a minute why. And the entire simulation is 500 microseconds, and we start with an empty near vacuum, I hope. Peter, am I correct? Yes. System, and we need some time to build up the plasma, and after that we have roughly 9.5 million particles. And we are interested in this stage after 200 microseconds, because as we inject particles, some disturbance happen in the plasma, and that manifests itself as spokes or arms that, based on the or due to the magnetic force, will turn around. So we have a rotational effect. And we want to measure these disturbances. And with this density probe, we will get these spikes when the spoke moves below or around the probe. And we get this periodic effect. So that's the physics part. So why is this important for computer? Because it takes time, okay? And this work was part of a larger plasma benchmarking effort. About 18 or 19 research groups participated. The actual project was led by Princeton University, and the Wigner was part of the study. If you're interested, that's the paper where the results are published. And each group brought its own simulation program, and the goal was to validate the simulation programs that they were correctly produce the same result. And this is the distribution or the range of the execution times. And if you can see, some of it took almost 2 months. So computer science comes in and challenge accepted. We want to speed up the simulation. Okay, so these are the different times from the different programs, and you can see that some of them are actually pretty good, 3 days, and one is actually very short, just 10 hours. So let's see what technologies they use. Most of it is legacy code using MPI clusters, large systems, and you can see some of them are very, very high number of cores, and still they don't really produce good execution times. The green ones are GPU programs. So they sort of populate the lower half, so they give better results than the others. And we can identify sort of clusters, the months, execution range, weeks, and days. And of course, we want to be in the days. So the big question is, which is our code? So we started with a GPU program, and you can guess it's not the best one, because I want to talk about performance optimization. So this is the baseline code that we wanted to check and improve, optimize. Okay, so that was executing in 12 days, and the others were significantly faster. So what is the difference? That's what we wanted to see first. So our code was basically a hybrid simulation code, and the time-consuming parts were implemented on the GPU. simple parts on the CPU. We used managed memory, and the entire simulation took about 12.5 million steps. So the problem is it's a sequential thing. It's an iterative simulation. So the steps have to be very, very quick if you want to speed up the program. And this is the profile of the GPU program, the first baseline program. And what we can see here is that this is one iteration step. So we need 12.5 million of these. And this is dominated by 2 GPU kernels. And the 2 kernels solve the Poisson equation. Obviously, that was the bottleneck. So we have to do something with that. But we can also see some red activity here, which is the unified memory. So that's also not very good. So we wanted to get rid of these first. Is the sound okay still? You can understand me. Okay. And that's just a zoom in version of the unified memory part. So we did a lot of optimizations, algorithmic optimizations and implementation-wise optimizations. The biggest benefit was changing the Poisson solver, but I won't say a word because Balint is the next speaker and he will give all the details of that part. And probably the trivial ones, we got rid of the managed memory. We did explicit memory management, moved everything to the GPU, so all the data transfer between host and device were removed. And we also optimized the diagnostics process not to slow down the simulation. So it was executing in an overlapped, host side thread. And I'm coming to the results. We measured the optimized version and the original version on different target GPUs. We used the original P100 and new ones, V100, A100, and the Quadro sort of workstation grade card. And we only executed the stable 100 microsecond simulation time. So we also did the full one, but I will show the results based on the 100 microsecond. And we have 3 versions, the original code, multi-grid based Poisson solver and the spectral solver. And that's the result. So what we can see is that the original code actually changed quite a lot just by moving it to a different GPU, which is obviously somewhat expected. But the V100, A100 difference is not much, but from the P100, it's a big, big jump. And then obviously the optimized versions show a big improvement. So this was 295 hours, and we went down to 50 hours. And the end result is 9 on the A100 and 7, 8 hours on the Quadro card, which is a bit surprising because it's not a supercomputer card, not a Tesla card. So I'll come back to that why. Actually, Balint will come back to that, hopefully. So this is the updated result. We still have these clusters. This is our code running on the V100, the original code. So actually, if we were to execute it on the V100, it would be side by side with the others. And this one down here is the A100 optimized version and the Quadro optimized version, which looks good. So we are happy that we are fast. So that's the result, but what's the word? Appetite comes with eating. So continue and try to optimize it further. So we want to use multiple GPUs. Question is, will it scale or not? Okay, I still have time. In the Wigner, they have 2 Quadro cards. So the first goal was to use those 2 cards and see whether we can halve the execution time. But then we thought, okay, why not try the Commodore where we have a lot more GPUs? So hopefully we can go up to 16. And why? Well, why not first? Because we just want to see how much we can push the system. But from the physics point of view, obviously the main benefit is that we can either reduce the execution time, so the, let's say research productivity can increase, or increase the resolution of the system so we can study larger problems. So luckily, physics helps. We have the superposition principle. So each GPU can work independently on particle partition system, and we just have to merge the density before the Poisson equation solver, and then we can continue with the next step. We used MPI for the general data distribution and also to support multi-node execution, and also NCCL or Nickel, the NVIDIA collective library for NVLink-based communication. And basically the key step is the all reuse operation before the Poisson solver. So let's see what happens if we increase the number of GPUs, what kind of results we get. So this is the original problem size. We had roughly 9.5 million particles, and on one GPU, the 100 microsecond simulation time finished in about 100 minutes. And you can see that sort of scales, but not ideally. So with 2 GPUs, we can halve the execution time. With 4, it's not really quarter and so on. The best result is about 25, 26 minutes, which would give, I think, for the full simulation, roughly between 1.5 to 2 hours. So that's much, much better than the others. Or maybe, no, 5 hours. No, sorry, with the 8, it's about 1.5, 2 hours. So that's the strong scaling. But if we increase the number of particles, then the situation gets much, much better. We give more work to the GPUs, obviously, and we can amortize the communication time. So this is, should have, yes, roughly 20, 40, and 70 odd million particles. And with the 70, it's almost perfect scaling. So we have strong scaling in that case, but if you look at this, we can use increasingly or double the number of particles and keep the execution time constant. So that's also good news. And I'll finish. This is a side project. Balin developed a real-time visualization for the simulation, so we don't have to wait 2 months to see the result. This is actually running on the laptop. So that's the difference that the GPU makes, paraphrasing the song. And so the results, to our knowledge, this is the fastest simulation program, at least in the Penning benchmark group. And I don't know about the others, maybe Peter can help, whether there are others, but we don't know. And there are many new opportunities because of the decreased or short execution time. There's a lot more space now for experimentation, changing different parameters, doing different physics. And the big goal is 3D, full 3D simulation. And we also want to extend the scalability study for larger supercomputers, so we can go up to 128 or 256 GPUs and see, for example, for larger grids. So we use the 256 by 256 grid, see what happens with the 512 or 1024 size grids and increase particles. So we can push up by our estimates to 1 billion particles, and hopefully it will scale to hundreds of GPUs. So thank you very much. That's all, and I'll pass on to Balint, who will talk about the Poisson solver development.